Hi guys, welcome to my YouTube channel. So before we get started, make sure to hit the like button, also subscribe to my channel. In this video, we will talk about quantum computing demystified, unlocking the potential. So make sure to watch the full video. Imagine a computer that could crack the encryption that currently safeguards all digital information from financial transactions to your personal identity, essentially breaking the internet as we know it. Now imagine this same computer could solve complex problems in a matter of minutes, problems that would take a classical computer many years to figure out. This kind of processing power could transform how the world addresses issues like climate change, drug development, national security, and food scarcity. This computer is a quantum computer, a machine that would revolutionize what computers are capable of doing. And scientists and engineers around the world are racing to develop the first full-scale quantum computer to unlock this potential. But the immense potential of a quantum computer is blocked by the immense challenge of developing the technology and science behind it. Quantum computing is more complex than classical computing because of the depth of the foundational science that underlies it. And there's still a lot of scientific work to be done before the world can go quantum. Which is where University of Wisconsin-Madison researchers come in. Researchers like Mark Erickson, John Bardeen, Professor of Physics and Chair of the Physics Department. Erickson has been working in quantum physics since 2001, tackling the underlying technology that could propel quantum computing. Erickson's research focuses on exploring one of the more promising approaches to building a quantum computer. One of the reasons it's so hard to develop quantum computers is that there's no clear and superior approach to building these machines. He explains, it's unlike the approach to building classical computers, which is well established and used by every major technology company. We don't know which approaches will be best for which parts of a quantum computer, or if there's one approach that will be ideal for all parts of a quantum computer, he says. The reason it's so hard to figure this out is that there are features of quantum computers that are incredibly challenging to develop. One key difference between classical and quantum computers is that, at the root of this challenge, today's digital technology uses the language of bits, which consists of binary signals coded with the value of a 0 or 1. This language powers everything from a Zoom call to a Google search, to streaming your favorite Netflix show. But in quantum computing, the bits are replaced by quantum bits, or qubits, which can be not just either zeros or ones, but can be both at the same time. This characteristic is known as superposition, and it's one of the reasons quantum computing has so much potential. There are exponentially more value combinations when you link qubits together. Harnessing that superposition quality is one of the key challenges of building a quantum computer, due to a core principle of quantum mechanics. In quantum mechanics, there's a fundamental notion that when you look at something or try to measure something, you disturb it. Explain Mark Safman, Johannes Rydberg Professor of Physics, who has also been working in quantum physics since 2001. If you try to look at or measure a quantum particle, doing so will push it and change it. Picture a coin spinning and landing on a table. If that coin was a qubit, and you looked at it after it landed, you would erase its superposition power to be either a 0 or a 1, and fix its value instead, which would eliminate one of its most promising qualities for quantum computing. This characteristic of qubits offers huge potential for writing algorithms that will power quantum computing, says Erickson. But it's a very fragile state. And one of the greatest challenges of quantum computing is finding a way to maintain a qubit's quantum state. Tackling this challenge is a main pillar of Erickson's work to develop the foundational technology that could enable quantum computers. Erickson uses silicon to make qubits and leverages nanoscale electronic systems to manipulate them. Silicon is used in classical computing, and he says that it offers the advantage of being able to apply some of the same materials and technology to a quantum approach. Erickson traps electrons in the silicon using tiny metal gates, much like in a classical computer chip, and turns the electrons into qubits. The small metal gates allow him to contain and control the electrons, which he can move around through a high-frequency voltage. He uses a magnetic force to assign and flip the values of the qubits between 1 and 0, similar to how magnetic force can be used to rotate a bar magnet between a north and a south pole. This is all done on a nanoscale level, which means he's working with a scale that measures materials by the billionth of a meter. He uses cutting-edge nanofabrication technology to do this work through UOU's Nanoscale Fabrication Center. Another key feature and challenge of quantum computing is quantum entanglement, which means that qubits can be manipulated to change values depending on the value of other qubits. This feature is what will enable quantum computers to run the really powerful algorithms that will elevate computing to the next level. But entanglement is tricky due to the fragility of a qubit superposition. You need to be able to change the value of qubits without looking at them or measuring them. It's really important to isolate qubits from anything that might change their superposition, Ericsson explains. But we need to create strong interactions between qubits because that's what powers useful algorithms. Ericsson's lab has done this on a small scale by placing the qubits 40 nanometers apart, which is so close that it's nearly impossible to comprehend just how tightly packed together they are. This proximity allows Ericsson to create strong interactions between qubits and entangle them. He has seen promising results through this method, but scaling it up is another challenge. We still have a long road ahead of us, he says. A usable quantum computer is years away by all accounts, but Ericsson's research trajectory offers a compelling example of how much this technology has progressed over the last 2 decades. When I started in 2001, we couldn't even contain 1 electron in silicon. Never mind turning it into a qubit, he says. Silicon qubits are one of the major kinds of qubits driving the conversation around quantum technology, and researchers at UW-Madison cover nearly the entire spectrum of relevant qubits. It's one of the many examples of the institutional strength in quantum computing at UW, says Ericsson. What do you think of our video? Let me know in the comments section below. Before you go, please hit the like button and subscribe to my channel. Thanks for watching.